My topic is planetary magnetospheres. I do teach this in my home department at the University of Michigan. It is such a broad subject that I have not had any success trying to do even an hour-and-a-half lecture that I could touch on maybe 40% of the topics. Looking at the library here, what speakers have done in the previous years, and I'm going to follow their lead, is to actually try to really convey to you the spirit of planetary magnetospheric studies, what the field is like, and go into some detail on the magnetosphere that actually is closest to the one that helps shield our beloved planet. And that is actually Mercury's magnetosphere, or so I hope to convince you by the end of the talk. So I have, there's one talk here, 30 minutes or so, and I'd like to break at that point, give everybody a chance to get a cup of water or whatever. And then I have a second one. So the first one is going to actually describe Mercury's magnetosphere. It's going to tell you about just some of the most recent results. It's also going to explain to you what space weather is for this planet. Space weather involves different phenomena at all of the planets. And courtesy of living with a star, I've been very fortunate to have a generous grant for the last couple of years. And I'm going to tell you what I feel I've learned about space weather at Mercury. Now, the second talk is also follows a classical path, and that's to take one plasma physical phenomena, in this case, flux transfer events. And I'll tell you what those are and why we should care about them. And I follow them across the solar system, if you will, from Mercury all the way out to Saturn. Okay, sound like a plan? So with no further ado, I need to at least set the scene. Thanks to the marvelous lectures, the lectures on the fundamentals that have been given here, I don't really have to do that much. The Earth, of course, is a medium-sized planet with a radius of 6,400 kilometers, give or take. Mercury, on the other hand, at first glance appears somewhat small. Its radius is 2440. I have to give all those digits because the PI for the Messenger mission was a geophysicist. It was 2438 before we arrived. So that may give you a hint as to why I don't do planetary geophysics. Actually, there were some big geophysical discoveries here. But the thing to notice when you look at this image up here on the right with Mercury is that people think it must have something to do with an interaction that took place during the formation of the solar system. But Mercury is a planet that almost not only doesn't really have a crust, it almost doesn't have a mantle. So you remember at one of the lectures yesterday, I'm sure you remember every number that was mentioned. The Earth's molten outer core, where the dynamo, the magnetic dynamo action takes place, is actually only about has a radius of only about 2,400 kilometers. Guess what? At Mercury, it's about 2,000 kilometers. And so actually, in terms of the region of the planet, where you have molten iron core that can support a magnetic dynamo, Mercury and the Earth are actually, if not brothers or sisters, at least first cousins. At first glance, you wouldn't think that was true. And actually, this leads us to the first of the great mysteries surrounding Mercury, which I cannot answer, and I don't think anybody has answered yet, and that is, why is the magnetic moment at Mercury so low? This is the one planet for which the dynamo modelers, instead of trying somehow to valiantly generate, some strong magnetic field that's been measured by spacecraft orbiting that planet. Maybe they don't think there's that much iron. The molten core appears to be small. The core, they think, might be half frozen for some reason. At Mercury, they're trying to dumb it down. In fact, having an equatorial surface magnetic field of only 200 nanoteslas is extremely difficult to achieve with an active dynamo. And without going into a lot of details, we know from the Messenger mission that we actually do have 2,000, plus or minus maybe 5%, we do have this 2,000 kilometer molten iron core. It's definitely there. We're not being fooled in some manner. But how you could have this still in a molten state and yet have convection, have the thermal gradients that drive the dynamo ultimately, the ultimate energy source, only generate a puny 200 nanoteslas, is giving that community a lot of challenges. Now, from the standpoint of the planetary magnetospheres, though, you learned today, you got extensive discussion of how of the factors that influence the size of a planetary magnetosphere. Now remember, as you go into, say, Mercury's perihelion, which is only 0.3 of an AU, that's about 60 solar radii. I mean, when you start doing things in solar radii, you know it's getting serious. You've got about an order of magnitude more solar wind ram pressure than you do at the Earth. And yet, the magnetic field that's standing it off, look at the tremendous difference in the surface fields. Now, in terms of the physics, though, it turns out that this 200 nanotesla, all by itself, if you take a distribution of solar wind pressures at 1 AU and you scale it to Mercury, in fact, about 95–97% of the time, that magnetic field is actually just sufficient to keep the magnetopause on the day side off of the surface. But what I want to point out to you is the typical standoff distance for the nose of the magnetosphere at Mercury is only about 1,000, maybe on a light breezy day, maybe 1,500 kilometers above the planet. What that means is that all the dynamics and all the action that's taking place at the nose of this little magnetosphere is occurring within about 1,500 or 2,000 kilometers of an iron ball. And all of a sudden you have a situation where the solar wind interaction starts to couple very tightly and immediately to this iron core. And in fact, I love the fact that in one of the earlier talks, instead of getting down into pressure gradients and diamagnetism or arguments like that for why the solar wind doesn't go into the Venus ionosphere or the unmagnetized part of Mars ionosphere, reference to a metal ball was made. Well, guess what? I actually do have a metal ball in this case, and so I'll be telling you a little bit more about that. Now, this is all great. You know, a magnetic field, small magnetosphere, you know, close to the sun. It doesn't have an atmosphere. It does have a so-called surface-bounded exosphere. You, of course, all know what the definition of an exosphere is. Definition of an exosphere says that the particles are basically on ballistic trajectories, and the chances of them interacting with another particle in the exosphere are, they should suffer no more than one collision during the course of one of these ballistic trajectories that brings it back down to the base of the exosphere. In the case of Mercury, and actually, as you go into the outer solar system, Ganymede, Europa, there's lots of bodies like this. They get these very tenuous atmospheres that are generated by a number of processes, including sputtering from solar wind and magnetospheric plasma. The exobase, it basically corresponds to the surface. So the surface itself is obviously not a collisional atmosphere. It's a surface. It's made up of regolith, which means more or less all of the junk rock that somehow cracked due to thermal cycling or volcanism a billion years ago, or asteroid impacts, you name it. They call all that gardening in planetary physics, by the way, which I think is pretty romantic for just, you know, debris being, over the billions of years, just being gradually, you know, powdered up. But in any event, in the case of Mercury, the ground-based astronomers have known for a long time that it has a beautiful sodium tail. Now, sodium is, of course, as you know from even possibly even high school physics lab courses, those D lines are very nice. They're very, very bright. And in fact, there's not that much interference because signal. I'm not an astronomer, but sometimes I impersonate one in the classroom. But I know signal to noise is often a challenge. You know, if there's a bright star in the field of view or something. But if you look up at this image here on the left, you actually see a measurement of fluorescence, if you will, of excitation and de-excitation of sodium atoms in the exosphere of Mercury. You notice that the ones that, at least with this color bar that you can see, are all downstream. What's going on is being illustrated on the right. Now, most of the neutrals, and by the way, it's not just sodium, it should be a whole host of fairly refractory materials. We've measured magnesium, calcium, telescopes from the ground have measured another 3 or 4 elements, but sodium appears to be dominant. Why? We have no idea. But in any event, most of these particles, when they're promoted, as they say, I like that, it sounds like they graduate. When they're promoted from the surface into the exosphere, most frequently this occurs because of either so-called photodesorption, namely a photon interacting directly with a crystalline monolayer somewhere on the surface. It goes all into solid-state physics terminology, so it starts to pour out at about this point if you go into the details. Also, thermal processes, thermal cycling. Some of the material that's in the exosphere, definitely we can see telescopically that it starts to appear as Mercury slowly rotates, the limb that's slowly rotating into the sunlight. But these guys tend to stay very low. They might only hop up 50 kilometers or at most 100 kilometers or so. And those guys just go up, and they're just like little, you can imagine, Walt Disney animation or something in soft music going, woo, boomp, woo, boomp. It's usually referred to by people that do the lunar exosphere, for example, or Mercury's, as hopping around. And if they hop somewhere where they're in a crater where they never see the sun, they can be trapped, and that's cold trapping. On the right, though, there are at least 2 processes which give a lot of energy to the neutral. One is if you have a micrometeorite, or for that matter, a larger one, that slams into Mercury's crust with enough energy to actually start disassociating fairly complex chemical bonds. Again, it's not the splash made by the micrometeorite, coming in. That actually isn't that energetic, or it's so undirected, it's very lossy. But when chemical bonds get broken, those can give you a directed energy. And if you can get up to a couple of an EV or a couple of EV, at the high end you can start to escape the planet totally. But at the very least, you may get up high enough, as we show in this right image, that depending on where you are in your orbit and what's going on in the sun, radiative pressure may push you back. Just as occurs in comets, you may wind up actually co-orbiting the sun with Mercury. And Mercury has this beautiful long tail. This tail, in measurements made from the Earth, is highly variable, and at least on some occasions has been associated with CMEs and other forms of transients. Again, micrometeorites hitting the surface, and also solar wind energy, kilovolt solar wind protons, are the 2 ways that they think most of this very, very high altitude exospheric material gets up there. All right, so as usual, if we're talking about the solar wind interacting, driving space weather at this planet, it has a magnetic field, and magnetic fields tend to shield the body. On the kinetic level, the particles come in, and they tend to execute like half a gyro radius, and then they go back out. Electrons go one way, ions go the other way. If you're doing the MHD treatment instead of the individual particles, guess what? You'll find that you get the current in the right direction for the magnetopause shielding current. And that's all well and good, but what opens up magnetic fields? What allows solar wind particles? What opens windows, if you like, or magnetic channels that allow solar wind particles to go down possibly all the way to the surface? And the answer is magnetic reconnection, magnetic reconnection, magnetic reconnection. And we knew, or it was predicted, I should say, before MESSENGER got there, that because we're in the inner solar system, and I'll talk about that actually more in the next talk, but we already knew that Mercury should be arguably the planet in the solar system where we see the most frequent and the fastest and the most impactful reconnection in the whole solar system. And I'll give you a hint, and that's because the interplanetary magnetic field gets stronger and stronger as you get close to the sun. It takes a little bit more than that. But that's the hint. If you look at this diagram, this was actually, I think, from one of our first couple of volleys of science papers. Essentially, every reconnection signature that we have at Earth, that the messenger instruments were capable of measuring, not only was present in our data, but it tended to be present on almost all of the passes. And it occurred far more frequently. And again, it tended to be far, far more intense. So just looking at this picture, for example, is there a pointer up here? I should have looked before I started. Aha. Okay, I'll try not to shoot any of the participants.
Thank you.
So, the magnetopause, when we don't have reconnection, the magnetopause in MHD is described as a tangential discontinuity. I promise not to do this every 3 sentences. How many, do most of you folks, are you familiar with rotational discontinuities versus tangential discontinuities in MHD? Hold up a hand, I see some nodding. Okay, all right, I just needed to calibrate a little bit. A tangential discontinuity is, when it's a tangential discontinuity, the short definition, not the rigorous definition, but the short definition is there's no magnetic field normal to this outer boundary of the magnetosphere. If there's no magnetic field normal to it, then the particles come in and the ions do a half gyro radius one way, the electrons do a much smaller gyro radius turn in the other direction, and the big picture is the solar wind just all flows away, just all flows around it. Magnetic reconnection comes in here, and it allows the interplanetary magnetic field to start, again, reconnecting, or in other words, merging. I'll show you some little illustrations later. It merges with the planetary field. And at that point, all of a sudden, the particles, the solar wind particles, a fraction of them, not only can go inside the magnetosphere, but they even get accelerated in the process. And I'll talk more about that. Now, at Mercury, at the Earth, normally the B normal to the magnetopause is so small that it's almost not measurable with the techniques that we have available. Like it's a fraction of a nanotesla, and our uncertainty in that component of the magnetic field, no matter what techniques we apply, is about a nanotesla. In Mercury, we see normal fields that are up to about 40% of the total magnetic field intensity just inside of the magnetopause. So when particles come up to Mercury's magnetopause, very, very frequently, they will, when they arrive, they will quickly find themselves on magnetic field lines that will guide them down to the planet. Again, where they can cause sputtering and they can start to affect the surface, or they can mirror and bounce back into the tail and go deeper into the magnetosphere. Do you see these little tornadoes? I never thought of that, but science wrote a piece, and they called them, first they called them tornadoes, then they called them magnetic twisters. At that point, I said, don't tell me anymore, it'll upset me. But these are flux transfer events, which we're going to talk about in a few minutes. All of the this is all collisionless. It's almost all frozen in magnetic flux, frozen into the plasmas that only breaks down where we do the reconnection. Otherwise, we couldn't reconnect. But the amount of flux that goes back, the flux that reconnects here gets pulled back into the tail. In the tail, so-called X lines and reconnection takes place there, and it creates it creates flux ropes that are not unlike the flux ropes that you see here on the surface. So basically, for people doing reconnection physics, it takes place in current sheets, and the question is, how does the process and how do the flux ropes that are created vary depending upon the nature of the current sheet, the conditions, the boundary conditions, the initial conditions, and the boundary conditions. There's a cross-tail current layer that just goes from dawn to dusk here. These are flux ropes rolling up in the tail current sheet. These are those same flux ropes. We call them flux transfer events taking place at out at the magnetopause. If you notice here, all these little dots, remember there's this neutral exosphere. In fact, inside of Mercury's magnetosphere, about 10% of the plasma is singly ionized sodium. And singly ionized sodium has almost is almost a zero fraction of the solar wind. So we know that it's coming from Mercury. It's not coming from the solar wind. So let's get back to that reconnection at the day side just a little bit more. I think this little moving illustration was made by ESA. We all use it because it actually embodies the definition of reconnection. One of the most physically meaningful and truly accurate ways of defining magnetic reconnection is that if you look here, see this blue field line and the red field line. I have heard one or two magnetometer engineers in my day say that magnetic fields generated by a spacecraft are of one color, and the ones we're trying to really study are of another color. But they were always just talking to other engineers or to people maybe that don't know too much electromagnetism. The fact is, the way that you separate magnetic fields is just by their intensity, their direction, and in plasma physics, the charged particles that are frozen onto those field lines, or the field is frozen into that particle population. So here in blue would be any magnetospheric particles in the outer part of Mercury's magnetosphere. The red coming in from the left, that would be the solar wind plasma. So this is the 1 kilovolt protons out here. On the blue, there's very, very few particles, but when we did look, if we were to look at them closely, we would see oxygen plus, we would see sodium plus. By the way, whenever you see these heavier ions, and they're singly ionized, the sun, you heard about those hellacious temperatures in the corona. The sun has a great deal of difficulty producing singly ionized anything other than hydrogen. I knew you'd like that. The fact is, they actually, in order to determine where solar wind plasma originates, they actually wind up looking at charge states at least up to what, plus 18, plus 16. They ratio these high degrees of ionization to actually study how different phenomena, how deep in the corona they must have occurred. Anyway, as this reconnection occurs, and these field lines shorten themselves, they accelerate the particles on both sides here, parallel to the magnetic field. They send them up and they send them down. But again, the particles, even though it's a new field line, two neighborhoods have been brought together now thanks to reconnection onto a single flux tube. They're now married to the flux tube, the new flux tube that they find themselves in. And so as the particles accelerate, part of them go up the field line, and they eventually get swept back into the tail, but they follow a rather long circuitous path. The ones that go straight down from here, they map down into these two magnetic cusp regions. And when they go down towards the surface, one of two things happen. One would be they could mirror. If they mirrored right here, then they would start, remember these field lines, if this were moving over here in a simulation, all of these field lines and all the plasma is going in the anti-sunward direction. So these are all moving backwards. So the particle comes down, it mirrors, and by the time it mirrors and comes back up, this field line has now stretched out to become this field line. So they go back here into the high latitude tail. This is called the plasma mantle region of the magnetosphere. Alternatively, if they slammed into the surface, they could produce sputtering. And if they produce sputtering, and part of the sputtered products are expected to be ionized, then those particles would now find themselves on a field that maps back into this mantle region. And if they have enough V parallel, to cancel out gravity, they can go up here and also contribute to the mantle. So this is, again, space weather at Mercury. It basically involves the creation of these planetary ions and of this exosphere through solar wind ion interactions with the surface. And guess what? A postdoc in my group, after doing about a year and a half of his 2-year fellowship, managed, and a great deal of creative data analysis, managed to pull out of our plasma composition instrument both the hydrogen plus, or if you like, the proton plasma mantle. So here's the day side to the left. This cusp is right about here. Spacecraft has a near polar orbit. It goes through this region, depending on what point we are in the mission, either 2 or 3 times a day. And that is the plasma mantle of Mercury. It's the first time we've mapped out this region, by the way, at a planetary magnetosphere other than the Earth. I suspect, though, your eyes are probably going over here. This mantle is all sodium plus ions. He tried very hard, but he can see O plus, he can see even magnesium plus. But the counting statistics are just so low that I think it'll just be a paragraph probably, or was just a paragraph in the paper. The paper came out just late last year. Anyway, we see both of these mantles. In the case of the protons, these particles could either have originated by being sputtered out of that crust, or they could be solar wind particles that mirrored. We could get H plus either way. Sodium plus, there is no sodium plus in the solar wind. So this is outflow. This is outflow from Mercury's surface. By the way, I'm not going to go into details of this here. Most of these particles are up near the kilovolt energy. And in fact, the sputtering models that we have right now suggest that they should be coming off the surface with even the sodium with just a few eV at most. And this is a very small volume of space we're working on, and it's possible that they've been accelerated. I mean, obviously they've been accelerated, but it's possible it could be wave-particle interactions. We don't have a proper plasma wave instrument on the spacecraft. And anyway, almost every rock that we have turned over, no pun intended, on Mercury with the MESSENGER mission has resulted in basically one question answered and 3 or 4 new questions occur. But there's nothing that unusual about that. Very quickly, that plasma mantle that I was showing you here. So these particles go along the magnetic field that threads the outer part of the magnetic tail. And even if you're not doing magnetospheric work, thanks to the talks on the fundamentals, you know all about this now. So these particles are streaming along the field lines. These field lines that you see up here do come out of a BATS-RS simulation. We've validated them pretty well. But as they go back, they E cross B drift, and we didn't get to see there should be a mantle up here mirroring it, but we didn't go up there. But all of these ions should gradually E cross B drift down into the plasma sheet, into the cross-magnetic tail current layer. By the way, people don't use that word neutral sheet anymore. The early magnetometers had such high noise levels and such poor digitization that they actually couldn't see that the magnetic fields out here in the plasma sheet, as you go through the current layer, they couldn't see that they became weak because of all the plasma pressure. But if you didn't have a non-zero magnetic field back there, then the plasma particles would all be lost down the tail. And we know that that doesn't take place. You wouldn't have substorms. You wouldn't have any of the dynamics we see. But they were so impressed with the weakness of the field that they declared it non-existent, and they called it a neutral sheet. But anyway, we usually just call it a current sheet today. But these guys E cross B drift towards the center here as a result of the dawn to dusk electric field that's imposed upon the magnetosphere by the solar wind and all of this reconnection. So for each of the particles that was measured, we could actually, for all of our traversals of each of the plasma mantle, for each traversal, we could infer an electric field, which was causing the plasma in the mantle to E cross B drift towards the equatorial plane. And from our knowledge of the width of the tail, we can calculate a cross-tail potential drop. Just looking at conditions in the solar wind, we sort of expect most of the time to be like here at, say, 15 to 30 kilovolts. And the data certainly support that. But here, all those potential drops, the best correlation with solar wind conditions is actually the magnitude of the interplanetary magnetic field. Now, this is unusual for anybody that does work at the Earth. There were a few of you that are doing some work for the Earth's magnetosphere. What is it? You always look for BZ south. So CME is coming, and you say, gosh, I know when it's going to hit. I just wish I knew whether or not we were going to go through the part of the CME that had some negative BZ in it. And I'm going to explain that in the second half of today's lectures. At the Earth, this is called the half-wave rectifier effect. The half-wave rectifier effect does not occur at Mercury. And the reason has to do with the nature of the interplanetary medium closer to the sun and the type of reconnection that occurs. So if you would just hold that thought. But here to presage that, here's a two-dimensional correlation where the potential drop is now shown in colors. So all these little dots, they look like That stuff that you flick on birthday cakes or wedding cakes at times. The reds, the yellow, reds, and orange, like you see right here, there's a few hiding around there, but those are the largest potential drops that are seen. Where do they occur? They occur when the interplanetary magnetic field was strongest and when the magnetic field was southward. So that north-south effect is still there, but the dominant factor is actually how strong the interplanetary magnetic field is. And again, just hold the thought. Just hold the thought till later. There were some discussions of magnetospheric substorms. I think this is the only chart that I've added to the talk. And this, of course, is for Professor Bhattacharjee and for Shinotani, wherever he might be. We do, in fact, see most aspects, most characteristics of these explosive energy releases in the tail. See, reconnection takes a lot of magnetic energy, puts it in the tail, and particularly if it puts it into the tail quickly, you wind up with an equally intense reconnection episode. Only thing is, when it happens in the tail, there's a different set of consequences to it than what occurs when it operates at the day side. Now at Earth, I think if you look at this profile in B magnitude, these are both passes through Mercury's, the lobes of Mercury's magnetic tail. And if you look down here, you see this is the growth phase. This would normally be about 30 minutes or so at the Earth. The first thing I'll point out, at Earth when we get substorms, usually 10-15% increase in the total field is more than sufficient to have wonderful northern lights and even a lot of injection of particles into the ring current region. I don't know if you could read the call-outs. There was a day when I would have been able to, but even I'm having trouble even from here. The magnetic field here at Mercury, it's not unusual for it to double during the substorm events that we see at Mercury. And if you remember that Shinotani figure, do you see how similar this is? Here's the loading, this little Eiffel Tower, as I sometimes think of it on top. That's actually a second-order signal that's caused by plasmoids forming in the plasma sheet underneath the spacecraft. And it produces a very fast unloading. And then you have at Earth, you'd have about 30 minutes or so of continued unloading after that. So at Earth, this is about a 60 to a 90-minute feature. If you can actually read the scale, at Mercury, on average, this is about a 3-minute feature. And the two reasons for this, one are the small dimensions of the system, but number two is the very, very high electric potential drop across the magnetosphere. And that, in turn, is being caused by the very high rates of reconnection. The reconnection efficiency, as the magnetospheric people, the forecasters use it, is up to about an order of magnitude greater at Mercury than it is at the Earth. This is not a substorm talk. However, I guess I added this figure too. I have to use these. This is an example of an energetic electron event at Mercury. These are the three components of the magnetic field. This is the inclination of the magnetic field in the meridian plane. This is Bx, By, Bz, B total. A lot of good work has been done by one of my students, Ryan Dewey. A lot of effort has gone into it, but he's actually been able to pull out energetic electron measurements up to 300 kilovolts with 10 millisecond resolution. And so everybody today is always touting their temporal resolution because of the magnificent instruments that are on MMS. But it turns out that this is coming out of a scintillation, out of an anticoincidence shield for a scintillator. Do we have any are there any experimentalists left? In my day, a group like this of people in graduate school, there would be like 2 of us that would hold up our hands. Is there anybody here who's an experimentalist? Okay, we're down to 1. Oh, 2. Hey, all right. Brothers and sisters in lab arms. An anti-coincidence shield. If you're trying to determine whether a gamma ray or whether a massless high-energy photon or else a particle with some physical mass went through your detector, how do you discriminate against one or the other? Well, what you need is a very, very fast. You don't have to measure You don't have to measure the qualities of the particle that you're going to reject with any great precision, but you do have to measure how quickly it traversed the core detector, whatever it was. And so here, because this was an anti-coincidence shield, we have 10 millisecond resolution, which is about a factor of 6 faster than MMS. On the other hand, the error bars on the energies that we get probably are 30 or 40%. But these are the energetic electron events that have been known to occur at Mercury since Mariner 10. Here we can see, though, that very frequently they only last for a few seconds. If we start looking at the magnetic field underneath, here you see a bipolar signature in the north-south component. Also, if you look closely there, you'll see that we are in the cross-tail current sheet. This is where reconnection takes place. That's the core field for people. I know there's a few people here modeling flux ropes in different places. That's the core field of the flux rope. It's directed across the tail. And gosh, Ryan, how many more of these did you do? Well, yes, the core field is so strong it actually gives you a peak in the total field, as you see at the bottom. And there, of course, is the energetic electron event. And the energetic electrons now, you can see, are actually right inside of this magnetic flux rope. I don't think we want to spend a lot of time on all of the charts that follow. But again, you heard Professor Bhattacharjee talking about work by Jim Drake and others on how flux ropes, both at the dayside magnetopause, for that matter in the corona, and also in the magnetic tails of the planets, how they grow by merging with adjacent flux ropes. So this is a particle code, so-called PIC calculation. Just look at the top traces here. If you're interested why they showed both, I could talk to you about it later. But if you look here, this is at time equals 14 gyro periods into their simulation, and you can see they call them magnetic islands because it's just 2 dimensions. But these are 2 flux ropes that have formed. Here they are just a little bit later, and you see how they've grown. If you look at other features, here, you can see similar growth. You can also see in some cases additional X lines are forming. They grow when they first form, when the current sheet first thins greatly, gets down well below the so-called ion inertial thickness, and the ions start to demagnetize. Then the growth is very, very rapid. On MMS, we're getting really our first look because the instruments are so high time resolution. We're finally able to get actually a look at these sub-ion inertial scale flux ropes. They grow from 2 mechanisms. One is continued reconnection at X lines that are adjacent to them. They keep adding additional wraps of plasma and magnetic field. But they also grow by coming together and basically merging with each other. And again, I think you heard the word coalescence in Amitava's talk yesterday or the day before. The bottom figure here is Jim Drake indicating that he can see a lot of T-parallel, a lot of heating and acceleration parallel to the magnetic field in the outer layers of all of these growing flux ropes. This is a much simpler diagram. This is the level at which I usually do theory. So for example, you have a small flux rope and you have a larger one. If they have the proper orientations, they come together, magnetic fields are oppositely directed. Remember, both of these ropes come out of the plane, they come out into the room. They're hanging above you. The smaller one here, wrap by wrap, it reconnects and gets added to the outer wraps of the larger flux rope. Now, when you look at that, though, if you have a string, and if you have a string, although it doesn't have all the properties of a proper magnetic field line, how do you wind up with how do you arrange it so that you have the maximum volume for a given length of the string? And the answer is it eventually becomes a circle. And indeed, for flux ropes, that's the minimum energy state. It's sometimes called the Taylor state. If any of you are working on this and you want to go into the original literature. But if you follow the length of these field lines right after they've reconnected, this is much, much longer than that. Folks aware of the first and second adiabatic invariants from a basic plasma physics course? Who knows what the second adiabatic invariant is? I see one hand. I'm not going to ask you to do a calculation, so you don't have to be fearful. There, that brought up a couple of more hands. Anyway, it's basically the integral of the magnetic or of the particle momentum parallel to the magnetic field over the length of the field line, the path length that's available to them. This is basically Fermi acceleration. And in fact, Jim in this particular diagram had been looking at how much first adiabatic invariant, which is just the magnetic moment, well, it's the perpendicular energy over the magnetic moment. This is of course the parallel momentum times the length of the path that it's bouncing back and forth along. And he doesn't find that much happening with the betatron. But because these outer layers don't see their magnetic field intensity change very much, but he does see very, very strong acceleration in those outer layers. And his image, and again, I think this was described day before yesterday, is basically early on you have a sea, if you will, or a current sheet that has broken up into a large number of all of these little twisted flux ropes. And every time they come together, they're boosting the energy especially of the electrons, because the ions are demagnetized still, you see, so they're sitting on the sidelines. And as a result of this, you continue to pump up their energies. And even at the Earth in particular, the source of all the 100 keV to actually 1 to 10 MeV electrons that we see in the Earth's tail has long been a mystery. And it's really wonderful to now be seeing at another planet, in the case of Mercury, situations where we can actually see, just like at the Earth, I believe the Chen paper for the Earth was shown earlier, we can actually see the same type of acceleration, albeit not with the comprehensive measurements that you have available at Earth, but we can see the close correlation between the energetic electrons and the formation of these flux ropes. Let's keep going. All right, this brings me to the core subject. It's not that long, but for this first part. So I've told you that space. Yes, sir. Go ahead. I think one more time. Principally, it's usually in the magnetic field measurements. There's very characteristic changes in all three components. And actually, did you get these charts? Were they put on the website? One of my graduate students, actually, he starts on Monday at Goddard. He graded for me a couple of times, and he put together what he calls a recipe book for doing reconnection-related data analysis with data sets like this. And in there, it actually has, at least when I do it, it's not just an eyeball identification that, I think the field was corkscrewing. I don't accept that. I don't want to waste my time. Because after all, every flux tube in the universe is a flux rope, right? By definition, if it's not a flux rope, it would mean that all the lines of force are perfectly parallel. And if the gods ever saw fit to create a flux tube like that, they would be the only ones who would be able to measure it with their perfect instruments. So in fact, all flux tubes, when you actually try to model them and work with them, they are twisted to some degree, no matter how hard you try, for example, in a fusion lab to make them parallel. But so for this reason, I work only with flux rope events and satellite data, which fairly closely fit one of two or three classes of flux rope. My favorite is actually just the Lundquist solution, which is one of the big family of force-free flux rope configurations. But again, that doesn't mean that those are the only flux ropes in the data set. Matter of fact, in some sense, almost all the magnetic field is part of a flux rope, over some volume. Did that answer your question at all? As I said, I appended it because this is a topical presentation, not on fundamentals. So I told you earlier that the main form of space weather that we see at Mercury is this interaction of the solar wind, of the particles in the solar wind with the surface to create this, this quite variable exosphere. And again, if there's any experts in, like in the lunar exosphere in the audience, again, the mystery is correlations are seen with CMEs and other types of solar wind events. However, at Mercury, we do know that day to day, it's primarily the photons from the sun and thermal effects that are promoting most of the neutrals into the exosphere. On the other hand, we still have events when a CME hits the planet, and if you will, it lights up. So this is the mystery of space weather at Mercury that we're working on. So I told you earlier that the solar wind, typical solar wind pressure, so at the Earth it's 1 or 2 nanopascals. If we just think about Mercury at perihelion, which is 0.3 of an AU, it's about 0.5 at aphelion. But it's about an order of magnitude, or if you insist, a factor of 9, higher than what we have at the Earth. And indeed, the typical solar wind pressures that we see in the messenger data are usually 10 to 15 nanopascals. And that's great. But what happens? What happens when we have far higher pressures than that? At what point do we actually have the magnetopause current sheet being pushed so close to the surface that the charge carriers actually encounter the surface? Because these current sheets are only very thin and they're only discontinuities in the MHD approximation. In real life, of course, they're doing their gyro motion thing. But we want to know that. We also want to know what the effect of reconnection is. In fact, be very nice to the people who, talk to the people in graduate school. A lot of you are in graduate school. So for example, the first paper I wrote as a first author in grad school in 1979, I took my Earth studies of reconnection at the nose of the Earth's magnetosphere, and I'd read a whole 3 or 4 papers on reconnection, and I boldly scaled reconnection to Mercury. And I said, gosh, reconnection for this little magnetosphere is going to always be exposing the surface of the planet to direct impact by the solar wind. And a really nice guy, Lon Hood, over here, that's his advisor, Jerry Schubert, well-known scientist. But Lon Hood, I saw him every day. I had no idea he was working on Mercury too. His advisor is anything in geophysical fluids, interiors, atmospheres, Jerry Schubert works on. And so I publish a paper, and 1 month in JGR, 1 month later, out comes this Hood and Schubert paper. And they start the paper off by saying, well, we don't know about this reconnection stuff. But they said, we do know about planetary interiors, and we're also proper geomagnetism people, and we know how to compute induction. And so they did the induction problem, and I'll show you some results a little bit later, but they said basically with the range of dynamic pressures that we see at 1 AU, it's almost impossible for the solar wind to ever overcome both the magnetic field on the day side due to induction and the intrinsic magnetic moment, or the field that is due to the dynamo. So there we are. If only, I don't know what would have happened if we chatted. Maybe we could have done 1 paper. I don't know. So I am going to show you how this, oh my God, so many solar cycles long discussion has turned out. I think with Messenger we finally see what's going on. Look very quickly. See, this is the iron ball. Do you see with this little quarter cutaway that I did, you can see the surface of the outer core of Mercury. So the diffusion time, and you're already told the answer to this in a couple of the talks, this is about the same amount of iron that we have at the Earth, So if the solar wind pressure increases by a factor of 100, and we decide that we're going to put magnetometers on the surface, and we're going to wait to see how long it takes for that compression to diffuse into this iron core, and maybe we get it. Maybe we're idealistic young scientists, and we said we want to know when it diffuses. We want to know when the dynamo finds out that that our sun just decided to put out a lot more solar wind, with a lot higher dynamic pressure. How long would it take? And so the number I saw in a couple of the talks was like 80,000 years for the Earth or 100,000 years for the Earth. The answer is about 30 to 50,000 years for Mercury. So basically, any studies that we do in our lifetime concerning the solar-wind interaction or dynamics in this little magnetosphere, whatever we do with the magnetic field above the planet, B normal on the surface of that core is only going to change by 10 to the minus I don't know what. Because essentially, with this kind of a diffusion time taking maybe 50,000 years to get to the center, changes are, B normal's only going to change, like you're going to be measuring it in atoms or femtometers or something like that. But what actually happens? So we push on it hard, and the magnetic field Alfvén waves follow the field lines. They tell the rest of the flux tube that there's this pressure, you know, ouch, I'm being pushed on really hard. And it gets down here, and of course, the field line along its entire length tries to readjust to a new equilibrium. But as soon as you get to the surface here, Faraday's law comes into play. As soon as you start changing B normal to this surface, even infinitesimally, what happens? An eddy current is set up. And the sense of that eddy current, and it all closes on the surface here of the core, that eddy current, and now I would probably invoke Lenz's law, is exactly with the sense that will oppose the change and will cancel it out. So what you see here, I've got yellow field lines. Those yellow dipole field lines are due to the dynamo deep in this outer core. But you notice these little green lines. Do you see they're all dipolar? They're exactly mirroring the shape of the dynamo field. That is the magnetic field due to the eddy currents. There'd be another circulation down here. That is these eddy currents that are reinforcing the field that is coming out of the dynamo. In fact, both of these current systems are inside the planet. So Mercury is actually the only one of the planets, at least I think it's the only one of the planets. We don't have detailed measurements at all of them. This is the only one where if you come to me and you say, I want to know the magnetic moment of Mercury to 3 or 4 significant digits. And they say, can you do that, Jim? And I say, yes, I can do that, but I have to know one thing. For what solar wind pressure? You're not accustomed in the case of the Earth or Jupiter or any place else being asked what is the solar wind pressure before you can respond with what is the intrinsic magnetic moment of the planet. But the reason here is because of these currents. By the way, as Mercury goes from 0.3 of an AU out to aphelion and the solar wind pressure changes, the magnetic moment on average goes up and down by about 5%. During large CMEs, we have changes in magnetic moment that I've estimated that go up to at least 30% amplitude. So it's really not nothing by any stretch. Of course, reconnection over here, I hate to quote that horrible old leader in Europe, but it doesn't care anything about the ethnic origins or what current system actually created these field lines. It says it's just going to reconnect them and let the gods figure that out later because it doesn't care. So reconnection is unaffected by the type, but having more magnetic flux put out by the induction does mean that if it's going to completely expose the surface, it has to reconnect more flux. So it either has to go faster or it has to take longer. All right, now we're down to the denouement here. So this is an example of a highly compressed, a pass-through Mercury's magnetosphere where it's highly compressed. So the average is 10 to 15 nanopascals. Here's 50 nanopascals. This is solar wind. This is the bow shock. Here's the magnetosheath. That's the magnetopause. That's about 300 nanoteslas of magnetic field in this compressed day-side magnetosphere. Mercury, the messenger orbit's almost polar. So you come in at the nose here, you're going to higher latitudes. Right here, you can just barely make out a little bit of a cusp. Closest approach is in this region. Then you go through the high latitude tail, and you go back down into the more and more distant tail as you go out over here. This is an example of what we call a highly compressed event. These range from about 30 or 40 nanopascals up to maybe 90 pascals. They don't quite make it up to 100. But if you look right here, we can see this is the dayside magnetosphere. Do you see this northward magnetic field? Those are those dipole field lines that you saw in the illustration a moment ago. So it hasn't been compressed out of existence. We still see it. Now take a look at this guy. I'm not going to show you Enlil movies, but Mercury was basically at the center of this fairly large, not the largest we've seen, but this fairly large CME right here. Our best estimate of solar wind dynamic pressure, we're now up to 140 nanopascals. So again, the average is 10 to 15. We're now up a solid order of magnitude. It's the same geometry. It's the same geometry. Here's the solar wind. Here's the shock. This is B total. This is that north-south component. Uh-oh. Where did the dayside magnetosphere go? The little red trace here is actually the smooth data. You can see as you get closer and closer to Mercury, closest approach is about in here, the fluctuations just become larger and larger in amplitude. In fact, I'll show you in a few minutes that most of these large amplitude fluctuations are actually magnetic flux ropes. It kind of looks like the entire dayside magnetosphere. Actually, as one of my students put it, this isn't so surprising. It's been run through a shredder. Only since it's an MHD shredder, our closed dayside magnetic field has been turned into a sea of flux ropes. And phenomenologically, it may not be that poor of a characterization. But look at this. Again, there's no dayside magnetosphere. Just get larger and larger amplitude. That's 140 nanopascals. Oh, wait. And the highly compressed events that I showed you earlier, we see about one of those a year. And this is for Mercury, this is for Messenger's orbit and everything like that. These guys, we saw we see two of the highly compressed per year. Those can be caused either by very intense high-speed streams or by smallish CMEs. These are all major CMEs. They occur about one per year. Now, if there really is no dayside magnetosphere here, we would expect to see that magnetosheath flow that we saw so nicely in the fundamentals lecture this morning. We should see magnetos just shock solar wind all the way through here until we get to the point where the magnetic field becomes strong. And what do we actually see? And there it is. This is an E over Q spectrum. For the protons. You see where there's a number of points in here, you'll see the flux goes a little bit higher than in adjacent points. And you can see it just chugs right along with a peak that's around a kilovolt, 1 to 2 kilovolts. Exactly what any planetary magnetosheath looks like in our solar system for a 400 to 500 kilometer per second solar wind flow. You can see that it's very, very hot. That's the width, the great width that you're seeing here. Sometimes it gets just a little colder right where the fluctuations begin. I almost wonder if there isn't a little bit of closed magnetic field, a little bit of remnant dayside magnetosphere underneath, and whether or not this could be a little bit of Bernoulli's law. I will be done in about 5 minutes. Anyway, as we get closer and closer to the magnetopause over here, you can see that the flux just keeps going up. And if we go to the composition, the sodium ions are shown here in this gold or yellow. The O plus is in the purple. And these are very, very large fluxes of sodium and oxygen. And where do we start seeing them? We start seeing them right in here. By the way, that mantle, I won't go into the details, but the plasma mantle we see when we go into the high latitude tail, it's always characterized by an energy dispersion. The particles with the highest energy, they run away down the field lines most quickly, and it's the slower particles we're left with. And you can see this downward going ramp. That's a very, very clear signature of the plasma mantle. And indeed, this is just where we finally go through the magnetopause and enter a region with much lower plasma flux and very, very strong magnetic field. That's actually just in front of the terminator plane. There's almost no dayside magnetic field present. Here's the next one. Here I'm going to skip the showing you that there's no northward BZ. Here we are at 180 nanopascals. And it's very much the same story. You see the fluctuations all the way through. Nothing until you get just in front of the terminator plane. Again, look at all of the sodium. Look at all the sodium. For this one, the shock's a little stronger, and you see a lot of heating right behind the shock. And then the other place where you see all the heating is right here before you go into the magnetosphere. And again, there you see the mantle. Here's the third one, 290 nanopascals. This is the, so there were 4 years of data, and we had we saw 4 of these these were all large CMEs. Very similar story, mantle, lots and lots of heavy ions being produced. And for the last one, which was more or less the same level of pressure that you see here, in other words, a major CME, the solar energetic particles were so intense that the noise levels rose in the plasma instrument so that we couldn't derive any detailed plasma measurements for that last pass. You know, I'm always envious when I see that old SOHO image where all of the CCDs are taking hits and their noise levels are going up, because in our particles and fields instruments we try to make them robust so that, you know, it just gets a little noisier as it goes on. But actually we have loops that are locked in there to track certain voltages in particles, and we tend to shut down catastrophically at a certain level. So I'm going to skip over that. So I've showed you that in the magnetic field, it does look like about once a year we see no dayside magnetosphere at Mercury. I showed you that on those occasions, it looks like we stay in all we see is magnetosheath plasma that's trying to make its way around the planet. This morning you learned about the bow shocks. Thank you very much for giving that lecture. We learned about bow shocks, we saw Sprader simulations and the like. So these are the trajectories for on those 4 passes that I showed you. The blue is when you're in the magnetosphere. The red is when you're out, and you notice on the day side, you're out the whole time. If you take the locations of where we entered and then later left the magnetosphere, and you rotate them around the sun-planet line, so you assume, to first order, that's all, a cylindrical symmetry. If you really have this solar wind coming in from the left, and part of it is hitting the surface, that's these black lines. By the way, this is offset because Mercury's dipole moment. Dipole is offset by about 2/10 of a planetary radius to the north. That's why it isn't a single surface of unit radius. There's 2 different ones. The low one here is the northern hemisphere, over which we have our closest approach of the spacecraft. The one that shows us below the surface, that's actually the southern hemisphere, which we don't approach very closely. But anyway, if the solar wind comes in from the left, and part of it's getting absorbed here on the surface, what do we expect to happen? Well, part of the streamlines don't have to go around the planet. They're terminating here on the surface. The shock doesn't get weaker because the shock strength is directly related to its propagation speed. And a bow shock, one of the conditions for having a bow shock is that it stands in the flow. So the Mach numbers of the flow dictate the strength of the shock. But if you get absorption, the shock should start moving in closer and closer to the planet as the amount of absorption increases. So even though we ran out of colors, this is the average bow shock. This is the average magnetopause. And for these 4 passes, the magnetopause actually comes down, the bow shock actually comes down, and it's at the location that we normally see the magnetopause. And if you try to extrapolate the magnetopause, it goes into the planet in the vicinity of the terminator plane. So this is the third check on the hypothesis that we have in fact detected intervals when we have the solar wind plasma going in directly to the surface. And so this is the summary plot now, which is sort of the guide for studying space weather at Mercury that's related to sputtering and the creation of this neutral exosphere. And this will be the breaking point. This is a little bit odd. This is actually due to Lonnie Hood, the other graduate student, him and Schubert. The vertical plot is solar wind pressure. Here, RSS is solar wind standoff distance. 1.0 would mean that we had a magnetopause crossing that was right at the surface. Now, how you can actually have one right at the surface, I'm not prepared to say. But if you could determine that, that would be at the surface. Here means that you must have encountered the magnetopause at higher altitudes because, in fact, at the nose, you would be below the surface. Here is where the vast majority of all the measurements collected at Mercury by Mariner 10 and Messenger, this is where we normally see the magnetopause. Out here, it's something like 10, 15, maybe 20 nanopascals. Those highly compressed day-side magnetospheres, where we still see a perfectly well-formed day-side magnetosphere, those are right in this region. They all stay just a little bit above the surface. There's no indication that they allow the bulk solar wind to get in. And these guys go up to about 100 nanopascals. But now we have this class up here. We have 4 examples that we got from Messenger. And for these are all CMEs. This is a mixture of CMEs and high-speed streams. And you can see we go from 150 nanopascals up to 300. This dashed line here is a model by Glassmeyer that includes the effects of induction. And so this is with induction and the magnetic moment determined by Mercury. He says that here around maybe 250, 260 nanopascals, we should be able to, in essence, compress all of the day-side magnetic field, even without reconnection, down into the crust. And that exposes the surface of the crust. This line right here is just that Chapman-Ferraro sixth root curve that you learned about this morning. The twist on this, though, is when this includes neither induction nor reconnection. But that also means that if the effects of reconnection are balanced by induction, the two effects, reconnection trying to trying to push the magnetopause down, and induction saying, no, you don't. If those two effects balance, then you would follow the Chapman-Ferraro curve that we have here. And these boxes that you see for each magnetopause crossing, that gives us the size of those corresponds to the dimensionless reconnection rate that we determine with minimum variance for all of these magnetopause crossings. And if you look, the smaller boxes are almost on Glassmeyer's line. As the boxes become bigger and bigger, meaning there's reconnection is faster and faster, they start to follow this Chapman-Ferraro line where the two effects are balancing. And over here, these folks not only have huge ram pressures, which for the top 2 here probably would be sufficient to drive the day-side magnetosphere to the surface, but in addition to that, they have some of the highest reconnection rates that we have inferred at Mercury. And went a little longer than I expected, but I'm available for questions. Should we declare a break, or would you like to chat a little bit? The other talk is much quicker, I promise. All right, should we stand adjourned for 5 minutes? Or? Okay. So what do you think? Is it interesting or too esoteric?
Too different from what I do.
What's that?
There's like too much information for me because it's really different from
Really different? Okay, I'll show you flux ropes next. The flux ropes will be a little... What happens to them?
Because the sodium ions should be like very heavy.
They are. In fact, we see about 10% sodium, but sodium has 23 AMU per.
Yeah.
So they constitute about half the mass density. So they're going to affect the alphane speed. They're going to affect the stress balance. So
No, I just think about.
they could be, and
So sodium.
we've looked for ions. We've looked for sodium ion cyclotron waves, but the wavelengths are actually comparable to the dimensions of the tail. So that probably isn't going to happen. Yeah.
So sodium ions that they exist in mercury.
Yeah.
The core of mercury, so which means that they.
And we see all of these different heavy ion species, and their gyroradii are quite large too. Yeah.
Yeah, because my research is on nitrogen ions, so I was thinking about how heavy ions, like.
Yeah. But for you and Raluca, do you see that? And Dan, do you see the outflow?
Yeah.
You want to
it's
see?
different, Yeah.
It's beautiful outflow data.
Yeah, this like I just want to know like if somebody is doing something about heavy ions, which means like maybe if I can read it and relate it to the nitrogen ions because.
Quite possibly. Quite possibly. Yeah, quite possibly.
Yeah, I'm just thinking about that.
That's great.
So there's somebody do the outflow of sodium ions in mercury.
You're looking at him, me and my postdoc. There's about 6 people working on this. I wanted to check if this is on time. Maybe we start to if we're doing a break now. It's either that or I could just leave it for the people to enjoy themselves. It's the one with the reconnection that I sent you about. I have to confess, I was hoping that some of the students that I'm expert in this, and so I started going slow and slow.
That was a bit of a fire hose.
And this is after I decided not to take the 2 talks and try to do 80 charts. If you look at the other planetary magnetospheres lectures in the previous schools, I felt it was a fire hose. So I didn't succeed in shutting the floor down. Not a glitch. I can do that. Well, yes, but remember though, so at Earth, so you get a compression here. It throws the magnetopause from 10 RE to 12. Actually, that only happens with lots of reconnection. Okay. Usually it's between 10 and 6, and it spends most of its time between 11 and 9. So it's way far. So if I'm out here and I'm shutting down the magnetopause, I'm sending nothing waves down to you. To tell the truth, I don't think the core ever really notices it. And at Jupiter, it's just about 100 times. But at Mercury, I'm like in your face.
But what about, say, the kind of events that CFC is looking at? Smooth events, electrical characteristics.
Well, actually, these basic, I don't think these are things in events. But we have our solar wind measurements are incredibly sparse. It's almost an accident. The instruments behind the sunshade, because we're getting 18 suns. Yeah, exactly. So so basically anything with it's like a solar probe, only not that bad. But it's still enough to fill our instruments. So we're crouched. The solar wind's coming right at us, and the one rule is you never can look in that direction.
Yeah.
So we only see a fraction of the distribution function. And velocity, I don't know, 5 or 10% of the time we can have a pretty reasonable guess of velocity. Because the temperature spreads the distribution function, pushes down the peak and spreads it. Temperature you can do a little better, but densities you just really can't do at all. But that'd be fine. So these are 2 spacecraft, and one of them is going to spend 3/4 of its, probably more like 9% of the solar wind. It's about conduction. So for Ganymede, all of the water worlds, Europa, Enceladus. The detection for all of that is almost all induction. So induction, no pun intended, induction is the hot new phenomenon for space plasmas these days. Although it's usually just associated with salty water. This is the only one I'm involved in.
So 215?
Yes, 315. Yeah, I like this. Did you have the students gotten these charts?
They actually have gotten these. Well, so
They may or may not know
if
it.
you look on, they don't know it. Yes. So if you look on the summer school schedule, some of the lectures that we've gotten, that we've been able to like pry out of the cold dead hands of the lecturer before they left.
Okay.
And Jim actually has presented his to us beforehand, so you can go find them on the web.
And again, it's in PowerPoint, but as a supplemental material, MHD discontinuities, minimum variance analysis, the Hoffman-Teller frame analysis, GS reconstructions, and I can prove that it was done by one of my students, because as you get halfway through, you see some very questionable, yes. He said that's how he feels about halfway doing a GS reconstruction. Anyway, if you do a GS reconstruction, you'll understand. It's a very, very nice technique, but you can spend a tremendous amount of time doing a single one of them. Okay, let's, anyway, all that's available to you. So that was an example of like a person comes in, Fran Bagenal, any famous planetary scientist, and they come in and they say, okay, I'm going to tell you everything that's new at the planet that I study. You know, 2 new missions have arrived there. The other way that it's used really is Planetary Magnetospheres does investigations. The other contribution that they make is kind of what I was trying to do in 2 minutes this morning with planetary ionospheres, and Jan Soika will do so much better over the weekend. And that is to pick a specific phenomena, like flux transfer events. Remember, those are those flux ropes that form in reconnection at the magnetopause, and here they are just getting pulled eventually back into the tail by the solar wind. So I was asked at COSPAR to talk about flux transfer events at Earth and all of the other planets. Yes? Oh, I'm sorry. Thank you. So what is a flux transfer event? A flux transfer event is a magnetic flux rope that forms due to forms due to reconnection at simultaneous reconnection at multiple X lines at the dayside magnetopause. The model that's accepted today was put forward largely on the basis of MHD simulations in 1985. And essentially, if you have n X lines, quasi-parallel X lines right here, and you have sheared magnetic field, in other words, magnetic field that's not perfectly anti-parallel to the magnetic field inside the magnetopause, the planetary magnetic field, and you reconnect these, what happens? You create spiraled field lines. This is how most flux ropes are formed. In fact, I was talking at lunch with a couple of students. I believe in a thin outer layer of the photosphere. It may be possible for velocity shear to also produce flux ropes. But that's the model where, you know, like as a kid, they take your arm and they twist it in opposite directions. That's the painful way of forming flux ropes. Usually they form as a result of the reconnection of sheared magnetic fields. To get a better idea of what this looks like once they've formed and they're being pulled back, this is an often used illustration. It is called the candy cane depiction. So again, one end goes down and connects to the cusp, goes down to the planet. The other end goes up to the solar wind, and then you have a matching mirror image on the other side that goes down to the other cusp. Okay. Why do we care about them? There's only 3 reasons that I can imagine that you should care about FTEs. Although there's been a friend of mine did a literature search. He was asked to do a review on this topic, and he said no. After he did a literature search and discovered there had been 1,000 papers, mostly phenomenological, published on flux transfer events, or FTEs, over the past 15 years. And yes, that was Jimmy Rader at UNH. I didn't blame him a bit. He said he would wind up with 20 friends and 980 people who would be very disturbed by his review, because there's just no way to review that many papers. But why do you care about it? First of all, of course, is fundamental plasma physics. Earlier, again, one of the earlier foundational lectures, you heard about how current sheets literally shatter due to reconnection and break up into, in many cases, large numbers of flux ropes. And this is often referred to as the so-called plasma instability, because originally in the tail we called all flux ropes formation, we referred to them as plasmoids. But the FTEs, again, it doesn't matter whether it's a flux transfer event, the magnetopause, or it's a plasmoid type flux rope forming in the cross-tail current sheet. The only difference is in the plasma parameters. You're working with a slightly different set of boundary conditions. I already described the plasma injection into the magnetosphere, namely into the cusps and then on to the plasma mantle that occurs as a result of FTEs. And then finally, even though it's not important at the Earth, it is very important in Mercury, though. These flux ropes do carry, there is a net axial magnetic flux. If you take your FTE flensing tool and you chop it on right off in a plane, create a plane that's or a cross section that's normal to the central axis of the rope, and you integrate the magnetic flux component that's parallel to the central axis, you will find that you're transporting a certain amount of magnetic flux into the tail. That's part of the so-called Dungy cycle. At the Earth, this appears to be absolutely insignificant. At Mercury, it may actually be dominant. So, this was a little bit about how FTEs are discovered. At the Earth, as soon as they started using analyzing their data in the so-called boundary normal coordinates, in other words, in the frame of the current sheet, they started noticing these interesting 1 minute or so long fluctuations that were very, very reproducible. And very quickly they, over the course of 5 or 6 years, they came to realize what they were seeing were either flux ropes, and these are probably the outer layers of flux ropes. You see this in-out, and then you see this right in the sheet, right in the region of most rapidly changing normal magnetic field. You see this little bump. You see this little enhancement perpendicular to it. These are the outer layers of flux ropes. And initially, they really didn't appreciate that at times they were going through the center of the flux rope, and at other times they were just going through, they were passing near one, and they were just seeing a little bit of compression from draped field lines. Apologies. There we go. Today, of course, the MHD simulations, in particular, simulations such as EPIC, which actually couple kinetic simulations, volumes that are governed by so-called PIC models in regions where reconnection is taking place, and they actually couple it both in and out of that region to a global MHD circulation. And you can see these flux ropes forming very, very nicely. This was a recent PhD dissertation at University of Michigan in Gambosi's group. Here you see an X line is forming. The experts, this is the magnetic field in and out of the plane. This is a cut through the noon-midnight meridian. These are flux ropes forming here, 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 and moving. Experts, reconnection aficionados. This change right here, this is the color bar. That's BY into the plane, that's BY out. This is the quadrupolar magnetic fields on either side of the X line, beautifully captured. That's for the 5 or 6 reconnection aficionados in the audience. Anyway, the flux transfer events, again, they're well understood, I think, now, at least in terms of their gross characteristics. You already saw this figure. The big thing that's different at Mercury is that they last only 2 or 3 seconds. They're only a couple of times the ion inertial length in the Mercury system. They're actually quite small, and we don't have any examples. It may be because the system is so small, and they leave the range of distances which we can observe with messenger so quickly that we never get to see them after they've grown a great deal. I talked to you about the exosphere and why we care. I was supposed to talk about what are the characteristics of FTEs that we see at the different planets, and why should they be different at different distances. And I think the reason why you would expect them to be different at the different planets all goes back to the variation in solar wind parameters with increasing distance from the sun. So this is 0, which I guess technically is the center of the sun. No planets down there, we hope. And this is 10 AU. Saturn is, of course, at 9. Jupiter's around 5. And then here's our friends, Mercury to Mars over here at the left. I've shown average dynamic pressure just because almost everybody needs that sort of as a framing parameter. But when we think about magnetic reconnection, at the end of the day, it's really all about the strength of the magnetic field and the strength of forces that are associated with the magnetic field. Now, there's 2 parameters we use for this. One is the Alfvénic Mach number, the speed of the solar wind divided by the Alfvén speed. You heard about that again today. By the way, if you square that, and you should do that, you see that all this actually is a ratio of the dynamic pressure of the solar wind to the so-called magnetic energy density or magnetic pressure, B squared over 2 mu naught. The other, of course, is plasma beta or beta, depending on where you're from. And this is the ratio, of course, of the thermal pressure to the magnetic pressure. You see here that over most of the heliosphere, most of the solar wind, it's a high beta plasma, not by very much, but beta greater than 1 is a high beta plasma. But then, all of a sudden, you reach the inner solar system, and it starts to dive down. And by the time you're at Mercury, it's decidedly a low beta conditions. Same thing for the Alfvénic Mach number. It tends to plateau out here, you can see, as you go to the outer planets. But again, it starts to dive down very sharply. By the time you're down here to Mercury, you've got an average Alfvénic Mach number of something only maybe 2, 3, 4. In the words of the old gas dynamicists or the aerodynamicists, this is sort of transonic. This would all be hypersonic. And all that really says is that in this region down here, magnetic pressures and the terms in the momentum equation that are basically driven by the magnetic field and the currents, they're rapidly becoming dominant. So for example, heating at the shock, as the Mach number goes down and down and down, the shock becomes weaker. The shock heating down here is actually very, very low. And as a result, we have very strong magnetic fields in the magnetosheath. For the outer planets, the Mach number is high. There's lots of heating, and you're starting with a higher beta. And so out here in the magnetosheath, you almost don't see any magnetic field. I mean, at least you have to, sometimes they even use a logarithmic scale. So ironically, even though the pressures are very low out here and you have these big distended magnetospheres, you see a huge jump in the magnetic field as you go from the magnetosheath into the magnetosphere. This is just a schematic on this. Dan Gershman is now, I guess, now tenured at Goddard. This was the first study he did after he got his doctorate and joined my group as a PhD. I don't think I'm going to spend much time on this, but again, at the Earth and the planets farther out, usually you see this big downward jump in magnetic field when you go through the magnetopause, and we're all taught to tell our professors that yes, that's because it's just plasma pressure here on the outside balancing magnetic pressure on the inside. On the other hand, as that Alfvénic Mach number comes down, you start to create this large region here, which we often call this a plasma depletion layer. The Mach number is very low. This is all getting to be very, very low beta. And as a result, the plasma is literally being squeezed off of these flux tubes as they drape around the day side. This is perfect for reconnection, and let's get to that point. And here we go. And actually, I could probably almost stop after this chart, because I think this is the important chart. This is one of those interesting things where what is old will be new again. People talked a lot about so-called symmetric reconnection and asymmetric reconnection about the time I was starting graduate school. I'd like to say in the late 1970s. The reason was obvious. They said, well, any reconnection model that I put together, think of, Sunnerup, Cowley, Tay, a number of others. They said, obviously, in the tail, we tend to have similar magnetic field intensities on both sides of the current sheet when we're in the tail. And they said, that's really pretty symmetric. But of course, all the dynamics inside the magnetosphere, it all starts with reconnection at the day-side magnetopause, loading the energy. That's what drives the system. And this is where the interaction with CMEs and all that good stuff comes into play. But typically, that's asymmetric. You go through the magnetopause, there's generally not that much plasma. Frankly, even at Jupiter and Saturn, there's not all that much. But then you go through, and on the other side, you see these very weak magnetic fields and very strong plasma pressures. So these are two examples here under very different solar wind conditions taken from the MESSENGER observations at Mercury. Both of these are day-side passes where we start up near the North Pole, where we're down at very low altitudes. Here, the closest approach to the surface is usually very near the cusp. This is the magnetic cusp where you see all these fluctuations, and there's a dimple, if you will, in field intensity. This is B magnitude. This is the north-south component. These are the counts for the sodium and the oxygen, and this is the proton data, the energy spectra. Anyway, so you're starting at low altitudes, and you're diving towards the equator. Both of these passes are fairly close to local noon. And as you dive down, you're going to higher and higher altitudes, and eventually you pop out into the magnetosheath. And immediately, if we look at these two side by side, this one here was during a large coronal mass ejection. During CMEs, everywhere in the solar system, we see very low alphanic Mach numbers. That's because of the very strong magnetic fields, both in the so-called plasma depletion layer, all that interplanetary magnetic flux that's draped around the head of the CME. And remember, CMEs actually have their own bow shock in front of them very often. And then you wind up with this pileup region right ahead of the CME proper. And then even inside, you often have a very large flux rope. And CMEs can wind up with very, very low alphanic Mach numbers. And of course, when they interact with Mercury, you wind up again with this very strong depletion layer. And I've had actually some students complain to me, Dr. Slavin, you've labeled that magnetopause, but look, the magnetic field intensity didn't change. I've got my notes here. Am I going to be tested on this? No. Only when we get silly and humorous do we say that. But if you look here, I've only included the BZ component, but do you see the shear in the magnetic field here? That's the magnetopause current sheet. On this particular case, the beta that we calculate just upstream, this is the magnetosheath side, the beta we calculate there was only 0.06. There is almost no plasma here. Now, if you look very closely at the energy spectra for the protons, you do see a shift right here. See this population right here? The energy is down. The flux is way the heck down. But that's solar wind. That's solar wind protons right here. And then you go inside the magnetosphere, and you don't see much. But what you do see is of much higher energy. Finally, when you go into the cusp, you see that characteristic. This is all material that's been injected from the magnetopause downward, like in that illustration in the previous talk. So over here, this is a high-speed stream. High-speed streams tend to have fairly high Mach numbers, or at least they don't decrease the Mach numbers. And so over here, there's no problem. This looks great. So over here, this is grand. You see the big drop. Magnetic plasma pressure here is very, very high. And up here you can see in the sheath, look at all the protons. So, this looks like Earth. This looks like, oh my gosh, over here. This is a beautiful example of symmetric reconnection. And the most remarkable thing when you look at this, and it takes a little bit of help maybe, what do we know from studies at the Earth? We all are brought up, at least in the phenomenological part of your courses, on the half-wave rectifier. So the forecasters here at HAO and at NOAA, they see a big CME and they say, wait, okay, nothing, plus 10 nanoteslas on the BZ. It looks like an old submarine war movie from World War II or something. It's still plus 5 nanoteslas, plus 4. No, hold on. Don't expect the auroras to brighten. Don't expect injections at geosynchronous orbit. And then all of a sudden, an alarm goes off as BZ in the solar wind goes southward. And so here we go. Here's minus 100 nanoteslas. That's minus, so this is beautiful. This would be, the alerts would be coming out of a NOAA if they had this data at the Earth. Actually, they'd really be coming out for a minus 100 BZ. And so that's the half-wave rectifier. Look over here. Actually, it's plus 100 nanoteslas. Okay, so nothing should be going on over here, right? But look a little closer. See all of these fluctuations here, all of these little bipolar sticks, bump, bump, bump. And do you see all the little upward transient increases? Those are all flux ropes. These flux ropes are occurring about 1 every 10 seconds. And this is for northward BZ. And you see, look at them, they never stop. And eventually they start to turn in, you lose the bipolar nature, and they just look like little diamagnetic decreases. We call these, and we believe that these are individual plasma injections coming from individual episodes of reconnection that create the flux ropes out here. We call these cusp filaments. And the cusp is actually the aggregate of all of the diamagnetic effect of all these little bursts of plasma that's being sent down into the cusp. And so this has incredible reconnection. All throughout this event, we've got reconnection going on with a huge amount of magnetic flux being sent into the tail, and that's with plus 100 nanoteslas. Over here we have minus 200. Yeah, there's a few little FTEs here, nothing anywhere through here. And look at this cusp. It's knocking the magnetic field, at least briefly, for individual filaments, almost down, down here below, well below 100 nanoteslas. Here it's just sitting there. There's a little bit of noise. You can see that there's some plasma that's been sent down. So here's the point, and we've known this actually for quite a while. For the importance of symmetric reconnection is that for any given shear angle, and you can think of it in this case as just the magnitude of your, how far your BZ is from being absolutely aligned with the planetary magnetic field. For any given shear angle, reconnection under symmetric conditions is always faster than reconnection under asymmetric reconnections. Further, reconnection can occur when you have true symmetric, and this is probably one of the best examples I've ever seen. For true symmetric reconnection, you can have reconnection for arbitrarily small, any non-zero shear across the current sheet. And that's actually a geometrical construction. If you sit down and you break the magnetic field, just do the geometry, you will see that if you have equal magnetic fields on both sides of the current sheet, then you have components that are anti-parallel for any misalignment, for any type of misalignment. And so here at Mercury, this is why we're seeing the effects, we believe, of reconnection all of the time. And it's ultimately due to these very, very low Alfvénic Mach numbers and the fact that it's low beta solar wind. Over here, when we get high-speed streams, we can get something that looks almost as lopsided as at the Earth. Most of the FTEs in the solar system actually are at Mercury. Our best estimate is that about half of the magnetic flux that's taken from the day side, put in the tail, and then returns, about half of it at Mercury is being carried by the little FTEs, as opposed to just the magnetic flux that reconnects and creates B normal before or after the actual creation of these little flux ropes. And since I was asked to cover all the planets, by the way, this just goes on all the time. This is the closest thing I think we have to a magnetosphere where kinetic physics is probably governing a lot of what we see. Again, FTEs, there's the magnetopause, just a little bit of a day-side magnetosphere. and then you switch over to filaments. But what I wanted to jump ahead to end the talk, we won't talk about the cusp filaments. What do we know about Jupiter and Saturn? So at Earth, we know we get an FTE every 8 or 10 minutes as opposed to every 8 or 10 seconds. And they don't appear to circulate very much magnetic flux. What about Jupiter and Saturn? This figure from a 1985 paper by Walker and Russell. These are all the FTEs that have ever been identified at Jupiter. I think there's 9 of them, and at least half of them are very sketchy, to say the least. This figure from these different passes by flyby missions just display the so-called B-normal component, the component normal to the magnetic field. And that's what people tend to look to first to pick out possible FTEs. And anyway, they're very, very infrequent. The Galileo mission would have been ideal for this, but unfortunately, the high-gain antenna had a failure and only partially deployed. So the magnetometer data from most of that mission was very low time resolution, and they did not find FTEs. And what about Saturn? There's exactly 1 paper on FTEs at Saturn. And so the situation is similar to the Earth. This is a postdoc from my group, also of last year. And these in purple, you see this. Do you see the bipolars up here? 1, 2, 3. These are actually compressions where we think we missed the FTE, but we could see the field draping around it. And then finally, we go through a magnetopause, and we see what can be modeled as a proper flux rope. So there it is, Saturn's only purported flux rope event. So this radial variation, I think, in solar wind parameters is probably very, very important. If we had more time for kinetics, there are 2 or 3 kinetic level mechanisms or considerations which might tend to suppress reconnection at Jupiter and Saturn. Whether it's all just the high Mach numbers there, or whether it's also these, for example, the diamagnetic drift mechanism or suppression mechanism of Swissdac, it's very clear that if you want to study reconnection, I strongly recommend that you go to Mercury. And if you can't get to Mercury, then join us on MMS. And simulations, even trying to span the scales to try to simulate CMEs, or excuse me, to FTEs at these outer planets is very, very challenging. Shinta Jha and the Michigan group just last week before last at MOP, showed their first attempt. I see some KH in it. I see some open field lines. I'm not really sure if they have an FTE. And the last thing here is for the whole heliosphere. Swadron and McComas a few years ago, they've had a hard time interpreting the magnetopause that surrounds the heliosphere. When Voyager went through, they didn't see the kind of fairly sharp discontinuity that they were expecting. And I got to give them points for boldness, and sometimes kind of crazy interpretations wind up being right. But it was very clever. Anyway, Swadron and McComas suggested that what if there was a giant FTE, that's just a flux tube that's due to reconnection is getting pulled out of the dayside heliosphere here of the sun. And they said, what if Voyager actually, instead of going through the heliopause proper, actually went right through a flux transfer event? Anyway, other than that, please remember Beppe Colombo. And I think in the foundational lecture, we kind of danced around the generalized Ohm's law. But if you, again, how many of you haven't taken your qual exams for your doctorates yet? Oh, so all the rest of you, you're either, how many of you are PhDs? Whoa, the school's changed over the last, what's that? Oh, those are PhD students, okay. Okay, that's fine. Anyway, whatever you do, if you're going to do a space plasma physics qual exam, I think I could speak for most of the schools. You'd better have a fairly good understanding of Ohm's law, including the generalized Ohm's law that is so critical to understanding the onset of reconnection. Thank you very much. I hope you enjoy the supplemental material. Please look at that too if you feel inclined. So I'll be here and I can take questions now, later, after the labs. I'll stay as long as there's anybody that is interested in talking. Excuse me? I thought I would. All right, all right.
Why don't we take 20 minutes, so we'll be back by 3:35, that's the best. And so just to prepare you emotionally, I'm going to change lab groups today. I'm going to do a little bit of you'll have to think about.
First of all, we don't know historically we have theories about what happens when we reverse it. Simulations and actually laboratory experiments. They have simulated dynamos in the lab now. It requires a sphere full of molten sodium about the size of the screen. And it's done at the University of Michigan, and I worked at NASA Goddard for a while, and I always worried whether or not my home was far enough away from it, just in case the plumbing gave out, because we only had some water or something. They must have had a safety plan. But anyway, so one group of theories is that the dipole just gets weaker and weaker and weaker, but it may retain something approximating its usual mixture of colloidal and zonal magnetic fields, and it just gets weaker and weaker, and then starts to grow with the opposite polarity. So that's really well behaved. Other people using a little bit of heliomagnetism data claim that when the field starts to really roughs a lot, all of a sudden it gets really funky and all